are preparing for your WAEC, NEC or GC exam, you should know that graph is a question that you cannot miss in any way. And so we want to look at this question on the graphical solution to quadratic and linear equation. And we have been asked to copy and complete the table for the relation y is 2x squared minus x minus 2 for this range of value, which we have been given the table that is pre-conceived already with some values inputted there. And then we have to use a scale of 2 cm to 1 unit on the x-axis and 2 cm to 5 units on y-axis to draw the graph for that range of values. And then on the same axis, we have to draw the graph of y is equal to 2x plus 3. And then we will use the graph to find the root of this particular equation, and then for the range of values for which this equation is less than 0. So before we just go ahead to start solving, let me just say something about this particular equation. If you look at that equation and what we are asked here, okay, originally we are given y to be 2x squared minus x minus 2. Now, as a rule of thumb, whatever subsequent question is coming from your graph, you should make sure that you tailor it to this particular equation. And in the very first case, look at what we are told for this particular equation. We are told that 2x squared minus 3x minus 5 is equal to 0. So for me to try and reflect y out of it, if I just take y out of this equation, I can say this is 2x squared minus x minus 2, okay? But what is remaining after taking this y out? We can see that we still have minus 3x, but we have taken minus x out, so we have minus 2x, such that minus x and minus 2x will be minus 3x, okay? And then again for the third term, we have taken minus 2 out, but what we have originally is minus 5. So if we have minus 3, minus 2 and minus 3 will be minus 5, so this is equal to 0. This is the manipulation that we need, and you can see that this in bracket is y already, so I can say I want to just write that as y. Then when minus 2x moves to the other side, it's going to be 2x. When minus 3 goes to the other side, it becomes plus 3. So the root of this equation is meaning that you should find the point where y, which was given as 2x squared minus x minus 2, is equal to this new equation 2x plus 3. So definitely you are going to have maybe something like this for the quadratic, and then something like this for the linear. Then this point of intersection, you can see we have the quadratic having that U shape, and then we have the linear having a straight shape. This point of intersection is what you need to trace to the x-axis, and that will be the root of the equation, okay? And then interestingly, the second one, the range of values for which 2x squared minus x minus 2 is less than 0. So most likely you will have something like this also. And then let's say this is the x-axis, and hypothetically, let's say this is the y-axis. So now for the range of values for which 2x squared minus x minus 2 is less than 0, looking at this graph, on the positive here, that is greater than 0. On the negative, this is less than 0. So the region of interest will be this region, talking about the quadratic, and then the range of values for x for which that is equal will be from here to here. So inherently what they're also asking is like, look for the root of the equation, okay? Because at that root, the graph is going to move on to the negative side, which is less than 0. So those are the things that we need to do, but our understanding is first and foremost key. And now that we understand, we can go ahead to say we want to solve the question as appropriate, which we are going to start doing with the table of values, okay? So now I prepared the table of value ahead, and I just put in all the values that we'll be needing as showcased in this particular case. Already we have been given the values of x, so that is reflecting on the very first row. These are the values of x, okay? We have also been given some values of y for the quadratic, and these are those values, 19 minus 2 and 26. But looking at the question, we have minus 2 as a constant. Minus 2 is not going to change its value at all, so that is there. But then this is for the quadratic, so this here is for the quadratic. Y is equal to 2x squared minus x minus 2, okay? This is for this quadratic. But that's not the only equation we have. We also have this linear equation, y is equal to 2x plus 3. So this will amount to y is 2x plus 3. So those are the two values that we have, and already we also note that 3 is a constant, so that value is not going to change, but we need to evaluate the value of 2x. So I'll just do maybe just 2 or 3, and then the other ones so then you can also get your hands dirty. You don't learn by just watching, you also practice. So you will do the other ones by yourself, because I'm just going to increase my speed and you'll not be able to see that. So in the first case, when x is -4, x squared will be 16, 2 times 16 will be 32, and make it the point of duty that don't forget your 2. Ensure that you include it in your equation, okay? When x is -4, minus x will be -4. The negative signs will multiply to become plus, so this will be 4, and the addition of this particular 3 values will give us the value of y here. And for us to do that, we'll say 32 plus 4 is 36 minus 2, that will be 34, okay? And then in this particular case, we can just use it to check if we are on the same track, and we're also going to get the answer correctly, okay? So minus 3 raised to power 2 is 9, 2 times 9 is 18, so we have 18 here. Minus x will be minus 3, and that will be 3. So 18 plus 3 is 21, 21 minus 2 is 19, so we are on track. That is quite correct. And then let me just do this as the last point, and I will just fill in the other ones. Minus 2 raised to power 2 is 4, 2 times 4 is 8, then minus 2 will be 2, 8 plus 2 minus 2 will be 8, okay? And I can just speed up now since you get the hang of it, okay? Now, in looking at the values of y that we just got, one thing I'm noticing was that this is not symmetrical. Generally, most of the times, with the values that you have, by the time you have your turning point, the values to the left and the values to the right, they'll just be reflective of one another. Like maybe you have, like if -2 is the turning point, then you have 1, then this will also be 1, you have 8, this will also be 8, you have 19, this will also be 19, you have 34, this will also be 34. That means that for this particular set of values, we are not having the turning point at all. The turning point is not included here. So students, just note that, so that by the time you are putting in your point on your graph, you notice that you need to be consistent with what you need to do. Okay, so we just extrapolate the values for this particular linear graph also, and then 2x will just be 2 times the value of x that we have. 2 times -4 will be -8, -8 plus 3, this will be -5. 2 times -3 will be -6, -6 plus 3, that will be -3. And I can just speed up now since you get the hang of it, okay? Now with this value, you can also notice that there is a consistency of an incremental value of 2 in this particular case. So it's going to actually be like that because it's a linear graph. It's going to be straight, it will be consistent in its differences. So this is our table of value now, and this is what we are going to use to actually plot our graph. All right, so here is our table of values that we just extrapolated out, and the questions we have to solve is the root of 2x squared minus 3x minus 5, which I have explained that is the point at which the quadratic is equal to the linear. And you can see here, if 2x moves to this left hand side, it will become -x minus 2x, which is -3x, and if 3 moves to the left hand side, it will become -2 minus 3, which is -5. So we need to look at the point of intersection of the two graphs, and then for the range we also solve that appropriately. But now we need to see how we can extrapolate our values for x and y on the graph. We have been told 2 centimeters to 1 unit on the x-axis. Here on the x-axis, 2 centimeters to 1 unit, and on the y-axis we have been told 2 centimeters to 5 units. Now for the x-axis, we don't have any problem because 1 unit, this is also 1 unit. We just need to look for means to actually locate that. So if you want to put that maybe here and just look at the center, let's say this is our origin. So for x we have 1, 2, 3, 4, and then -1, -2, -3, and -1. You can see that is quite good. Now for the y-axis, 2 centimeters to 5 units, meaning that between 2 centimeters, between this point and this point, this is actually 2 centimeters. And those 2 centimeters is comprising of 10 small boxes. So inherently we are saying 10 boxes should be 5 units. 10 boxes, we are saying it is 5 units, okay? Then if that's the case, what is 1 box? What is going to be the unit of 1 box? That unit of 1 box will be, here we just need to cross multiply, okay? So we are going to have it as 5 times 1 divided by 10, and this is just 5 here 1, 5 here 2, so this is 1/2. So each of the small boxes is going to be 0.5 units. I'm doing this because I need to extrapolate numbers that are not going to lie directly on the tick boxes, because 5 units we only have 5, 10, 15, 20, 25, 30 and co. But here look at this, we are even having 34, 19, 18. We don't even have anything that is a multiple of 5. So we need to know how we can appropriately adjust that. So if I just want to read it off and show it on the graph, I will say for me to get each incremental value, so here this is 0, and then reading on the vertical axis, this will be 0.5, so this is 1, this is 1.5, this is 2, this is 2.5, this is 3, this is 3.5, this is 4, this is 4.5, and this will be 5. So I can have 5, 10, 15, 20, 25, 30, 35. Okay, so the point at which I'm taking the graph is quite good. That is quite interesting. I think that can be useful. I can use this as my origin. I didn't mean that my 35 is eating up, then I know that I need to move my graph down, but I think with this is quite okay. I can just input that and I will draw my vertical and horizontal axis and put in the scale. I will go ahead to solve the question. All right, so we have our graph prepared already with the scale that we're given and placed on the graph in such a way that everything will be centralized as appropriate. And then want to extrapolate those values. In this first case, for the quadratic equation, when x is minus 4, y is 34, and I've been able to establish the fact that now in this case this is 4. Okay, 34 will just be 1 unit before 35, and 1 unit will correspond to 2 boxes because each of the small box is 0.5 units. So we are looking at something here to say this point of intersection is a point of interest for us when x is minus 4 and y is 34. So we can note that here. Okay, and again we can look at the value of x minus 3 and y 19. 19 will also be 2 boxes before 20, so we have somewhere here. So that point of intersection is also our point of interest, which we will note now. So here, that is 19. And then since we get the hang of it, you can just go ahead. Minus 2 and 8. 8 will just be... You can just get the other ones. I will speed up the video now. Okay. So if you do that correctly, you are going to have something like this as the curve that is joining all of your points. Okay. And then as good as it gets, you can also do the same for the linear graph. Like here, when x is minus 4, y is minus 5. You can see this is minus 4 here. And then we can look at minus 5 here. And this should be quite straight because it's going to even be a straight line graph. Okay, so we can say this is our point of interest. And when x is minus 3, y is also minus 3. Minus 3 will just be... mid here is 2.5 plus 1 box, that will be minus 3. That will be like here. Okay, and then we can just continue. So when x is minus 2, it is minus, y is minus 1 here. When x is minus 1, y is 1. This is exactly the same point. And interestingly, here, that is the point where the value of y for the quadratic and the value of y for the linear, they are overlapping. So that is still the same one that we have notched initially. You can just get the other ones. I will speed up the video now. Okay, when x is 4, y is 11, so that is 11. And then we can say we want to join them all with a straight line, just passing through all of them. And then I think this is as good as it gets. Okay, so that is our graph. And as a rule of thumb, it's just good that you label here, this is a quadratic, y is 2x squared minus x minus 2, and this is the linear, y is equal to 2x plus 3. All right. So in the first case, where we are asked to find the roots of the equation 2x squared minus 3x minus 5, which we have explained to be the point of intersection of the quadratic and the linear graph, you can see here this point, and that is minus 1. Okay, and here this point, because if we trace that down, we are going to see that it's going to land directly between 2 and 3, and that is 2.5. So here is down on minus 1, which we even got from the graph initially. So you can just say the roots of that equation are x is equal to minus 1 and x is equal to 2.5 as seen from the graph. Okay, So students, you can still go ahead to verify this answer by solving for this question, maybe by factorization method or formula method, to get the root of that. But here, let me just make use of the calculator to say I want to equate the two equations together, like I have 2x squared minus x minus 2 is equal to, that equal to will be alpha calc, okay, is equal to 2x plus 3. So I want to solve for this. So I'm using shift calc, that is solve. And I want to solve for x, starting this iteration from 0. No, I have two values, one in the negative, one in the positive. So I will take minus 4 as the first point to start this iteration. Start from minus 4. What is that going to give me? Okay, x is minus 1. That is for this. If I still want to solve, I want to use 4. Okay, let me just use 3 now. I want to use 3 as the starting point for his iteration. Then what is that? So you can see 2.5 and minus 1. And that is giving me the hint that I am quite on track with this solution that I've got. But that's not all. For the graph, we also have to find the range for which y is less than 0 for the quadratic. And in that particular case, if we are to look at it, we can look at this. These are the points where y is actually less than 0. You can see up here we have the positive values of y. Y is greater than 0 there. Down here we have the negative values of y. Y is less than 0. And then we are asked to find the range for that particular case. If you zoom in, you can see that here and here, those are the points that we have as the range for which y is less than 0. So you can say we want to get the particular range as shown on the graph. Now, on the horizontal axis, we have 10 boxes that are amounting to 1 unit. So each of the boxes is 0.1 unit. And here, we have 2 boxes just before 1. So that will be 1 minus 2 of those boxes, which will be 1 minus 0.2. So that will be minus 0.8, negative because it is to this side. And here, I can see it's just between 1.1, 1.2, and 1.3. So I can say, let me just say this is x less than or equal to 1.25. Okay, that's what I'm seeing as that. But actually, this is also the root of the quadratic equation where it's cutting the x-axis. And we can also say we want to solve for that. We can just say we have our equation, okay, 5. We want to solve it is a quadratic, that is amounting to 3. And what is the first term? That is 2. And then the coefficient of x, that is minus 1. And then the constant c, that is minus 2. So you can have the calculator to solve that. And then the very first solution, x1, this is 1.28. That's quite interesting. You know, we got 1.25 close to 3. Okay, and then the other one, this is minus 0.7, which is approximately minus 0.8. And then okay, it's also giving us the minimum value of x and the minimum value for y. We are not concerned about that here, but we have just verified that yes, within this range of values that we have, we're actually quite on track and our solution is done and dusted. So students, you can do well to practice on this type of questions a whole lot, particularly because there are sure bankers in your exam, and proper preparation like this will prevent poor performance. We hope this will be useful for you and wish you the very best. All right.